So now what we want to do is look at reconstruction. So as I've mentioned, what we expect to do intuitively is remodulate the channels, put them back to their normal carrier frequencies, the bandpass center frequencies, and then add them up. Just add up the filter bank output, right? And if there's no hop, if we're sliding, if R is equal to 1, then that's just got to work, right? And we actually proved that it worked in the case of DFT because the DFT is exactly invertible and we know that works. And we saw the form of the inverse DFT in this sum, because remodulating and summing looks like an inverse DFT, except for the 1 over n term. So the 1 over n is just a normalization, and for filter bank reconstruction, that's optional. You can allow a constant delay or a constant scale factor in a filter bank sum and still call it perfect reconstruction. So now in the overlap add world, we had that the reconstruction was perfect if and only if the windows overlapped and added to a constant. So this is a time domain constraint on the overlapping windows used. And so for the rectangular window, that's trivial. You just always get it for rectangular. For anything in the generalized Hamming family, you get it for 50% overlap and so on. And so, and the way we derived that was just adding up the frames, right? The DFT of the frames, the TFT of the frames, if you just sum them all together, you get back your original signal. And so what we did then is test the reconstruction of the filter bank sum and derived a dual condition. So we conjectured that we should be able to take our channel signals, which are all at baseband, remodulate them with an e to the j omega km, and m is our time index, which is the same as n here because there's no hopping going on, r equals 1. And then we're just summing over channels. So the sum from k equals 0 to n minus 1 is just adding all these complex bandpass filters together after you put the carrier back in, right? So if there were a 1 over n in front of this, it would be exactly an inverse DFT, right? So, so we're confident that this is probably going to work. And so what we did then was plug in the definition of the STFT, which is right here, just the standard STFT definition, interchange order of summation, and got this interesting impulse train out of the complex sinusoid sum. So we got this impulse train, and we applied the so-called sifting property of the impulse to reduce it down to one sum. And so you just sum over the points where the impulses are 1, the impulse train is 1, and you get this sum. And it's an overlap add of the input multiplied by the flipped window. And here's that factor of n that we get because we need a 1 over n normalization somewhere. All right, and then we noticed that, well, you know, if this window, if we enforce zero crossings in the flipped window, every multiple of capital N samples, which is always true with every window we've seen, then you only get one term out of that sum. And that term is multiplied by, W of 0 and capital N. And so this is a so-called Nyquist property for the window, that it has these particular zeros. And it's exactly the Fourier dual of what we derived for the overlap add case. Because in the overlap add case, we are summing together a bunch of transforms. In this case, the filter bank case, we're summing together a bunch of bandpass signals. So it's the Fourier dual.